In this video for Computer Science 9618 A-Level, we're going to be taking a look at section 16.1, which are the process states and the scheduling algorithm, specifically shortest job first come, first served, and shortest time remaining first. So let's go ahead and take a look at our learning targets. They want to show understanding of process management, multitasking, and what a process actually is. The process states, there's running, ready, and blocked. So we're going to go over those, scheduling and the function and benefits of different scheduling routines, which we're going to go over too. So let's jump in. When we talk about a process state, what does that mean? Well, a process control block is a data structure that contains all the data needed for a process to run. But what do we mean when we say process? Well, process means a program that is in the state of executing, and we call this dynamic. A program is written code that is not running, and it's considered static. That source code is not running. There's no changes being made from the user. There's no input. We call it static. When a program is running, we call it dynamic because it's receiving input. We do input, process, output, those three states for a program that's in the state of running. Now, there are three states a process can be in. The state it is in is called the process state. Now, a job can only be in one of these three states at any given time. It can't be partly in one state and partly in another. It's going to be in one of these three. It can be in the running state, which means it's a process because the source code for the program is running. It can be in the ready state. It's waiting for its turn to be used by the CPU, or in a block state, and we'll talk about what that means. Now, these process states are determined by the high-level scheduler and the low-level scheduler, and we'll talk about what those do in just a few moments. All right, so a job or task can only enter the running state from the ready state. So if it's in the ready state, it can go to the running state. That's the only state it can go to. Now, a process's turn to use the processor, that's what we mean when we say it's in the running state. The operating system scheduler allocates CPU time to the process so it can be executed. And remember, a process is a program that's currently in the state of running. Now, we can go from the running state back to the ready state. So the program is executed during its time slice. That's why it's called a process. When that time slice is completed, an interrupt occurs and the program is moved back to the ready queue so it can wait its turn to run again. Now, when it's in the running state, it can go to the blocked state. The process needs to carry out an input-output operation. So it's running. We need input from the user. It's going to move from the running to the blocked state. The operating system scheduler places the process into the blocked queue. When you're in the blocked state, you can go back to the ready state. The process is waiting for that input-output. The input-output is ready to be completed by the process, and we can go back to the ready state. You cannot go from blocked to running. Now I have a diagram that will make this a lot easier to understand. So a program can enter the system, or it can the process can end when it's time to exit the program, such as application.exit or reaching the last line of code. There are three states a process can be in. It can be in the ready state, can be in the running state, it can be in the blocked state. When a program enters the system, the process is getting ready to run, but it has to be ready before it can do it. Once it's in the ready state, the only place it can go to is the running state. When a process is running, its time has been allocated by the CPU. It is executing. If it reaches the last line of code, or you get to application.exit, the process ends. It exits the scheduler because it's done. It doesn't need to continue running because it has finished. Now, the other place it can go to is the block state. If the process is running and we need input from the user, it's going to enter a blocked state. If its time is done and its allocated time is done, then it's going to move back to the ready state. So with running, we can go into the block state, or we can go back to the ready state. How do we know? Well, it depends on whether or not input needs to be used. If we're in the block state, we cannot go to running. The only place we can go from the block state is to the ready state. Now let's talk about the high and low level scheduler and how it actually works and take a look at another diagram. So there are two queues you need to know along with the high level scheduler and low level scheduler. The ready queue, this is about the ready state. Processes placed into the ready queue, they're done by the high level scheduler. Now the low level scheduler moves it from the ready queue, from the ready state, to the CPU to be placed into the running state. So now that it's on the CPU, it is in the running state. It can finish going back to the ready state, or it can go back to the ready queue by the low level scheduler upon exiting the CPU to hand off to the high level scheduler. And now I have an illustration to help make this a little more clear. Now the blocked queue, that's about the block state. Processes placed into the block queue, this is done by the low level scheduler. These are waiting for the input output resource. It's waiting for input by the user. Now when it has completed, the high level scheduler picks it up, moves that process from the block state back into the ready queue, which is the ready state. Now the block queue is also known as the backing store. So if you're taking a computer science course later on after you leave the Cambridge program and you go to college, you may hear them talk about the backing store. That is the blocked queue. Now you may hear someone talk about the medium level scheduler. All that means is we're going to swap jobs or tasks, these programs, between the main memory, which is the RAM, and the backing store, which is the blocked queue. That's what the medium level scheduler does. Now let's take a look at this diagram. So this is from the Cambridge book. I believe in giving credit where credit is due. And you have this book. Hopefully, if not, snap a picture of this. Education should be free. But anyway, let's move on. So P4, P6, P5. What does that mean? That means process 4, process 6, process 5, and process 3. So we have 3 or 4 different processes running. Now, the high-level scheduler puts it into the ready state. So P5 is next, followed by P6, followed by P4. Remember, a queue works on the first in, first out principle. Now, the low-level scheduler is going to say, hey, P5, it's your turn. Come this way. It's now in the running state because the CPU is going to allocate the time. Now, when it's in the running state, if it reaches the last line of code, or application.exit, it's going to finish and it's going to leave. If it's waiting for input from the user, the low-level scheduler is going to pick it up from the running state and put it into the block state. What's the queue that holds all the processes in a block state? We call it the blocked queue, also known as the backing store. Now, if we are not waiting for input, then we're going to go from the running state all the way back to the ready state. So it's going to get passed off to the high level scheduler, and the high level scheduler is going to say, okay, I'm going to put you back at the end of the line. So now that we know how the high level and low level scheduler work, as well as the states, we got to talk about those scheduling algorithms. Now there's some vocab you need to know that will help make you successful when you're calculating these. When you're doing the scheduling algorithms, it's all about what is the most efficient, and you do that by calculating the wait time, but there's other things you need to know in order to get the wait time. The first thing you need to know is process. You need to know that is a program that is running. If you don't know it's a program that's running, you may not know what they mean by process. And on the exam, they may say, give the difference between program and a process. Well, a process is a program that's in the state of execution. There's also burst time. Now, this is how long it takes to complete a process. Remember, a process, a program that is running. I cannot stress that enough. Arrival time. This is when the process arrives to the queue. Exit time is when it finishes the process, but arrival time is when it enters the queue, not when it enters onto the CPU. Make sure you understand the difference. So exit time is when it finishes the entire process. There's not going back to the ready state. It is done. We've reached the last line of code. We've reached application.exit. Arrival time is when it arrives to the queue. So make sure you know that. Turnaround time is exit time minus arrival time. This is why you have to figure out the correct arrival time and the correct exit time, because you got to calculate turnaround time. Well, why do you need to know turnaround time? So you can get the wait time. And the wait time is turnaround time minus the burst time. Now, you need all of those. There are 3 scheduling algorithms or routines that you need to know. The first one, and these can be in any order. They're not, a special order here. They can be in any order. First come, first served, shortest job first, and shortest remaining time first scheduling. So those are the abbreviations. So we're going to talk about each of these and look at examples. All right, first come, first served. This is considered non-preemptive. We'll talk about what preemptive is and just with another scheduling algorithm later on. Similar to the queue concept that uses the first in, first out principle. The first process in the ready queue, that's the first one to exit. That's the first one to be served. So the data added to the queue first leaves the queue first. We're going to calculate the wait time for each process. That is what we are after because this will allow us to solve the average waiting time. When we have the average waiting time, we can figure out which scheduling algorithm works best. So let's take a look at the first one using first come, first served. You can see we have 4 processes. Process 1, 2, 3, and 4. We can see the burst time, which is how long it takes in order for it to fully complete before it reaches its last line of code. Then we have the arrival time, when it arrives to the queue. So P1 arrives to the queue first. We're going to let it run until it is done. Well, it has a burst time of 15 seconds. It arrives at 0. It finishes at the 15-second mark. Now, is it really seconds? No, it's a lot less than that, but we're going to use seconds because it's easy to illustrate. So P1 is done. Now, P2 was the next one to arrive. It arrived while P1 is running because it arrived at the 1-second mark. We're going to serve P2 next. We can see it has a burst time of 8 seconds, so it finishes at the 23-second mark. P1 and P2 are completely done. What was the next one to arrive? Well, that was P3. We can see it arrived right after P2 and arrived before P4. So because P3 was next, we're going to handle that one. It runs for 19 seconds. That puts it at the 42-second mark. The only process left is P4, and that's going to run, and it runs for a burst time of 7 at 49. Now that I have these numbers, I can calculate the exit time. I need the exit time so I can calculate the turnaround time. I need the turnaround time so I can finally calculate the wait time and then use the wait time to calculate the average wait time. Does it seem confusing? It's not. Let's break it down nice and easy. Exit time. This is when the process actually finishes. Let's take a look at process 1. When did it finish running? It finished at the 15-second mark. It never ran again after that. It was completely done. We look at process 2. That finished at the 23-second mark. That is when it was completely done. Process 3, when was it completely done? That was at the 42-second mark. And what about process 4? When was it done? At the 49-second mark. Now that I have that, I can calculate the turnaround time, which is my exit time minus the arrival time. So I look at process 1. What is 15 minus 0? That's 15. What about 23 minus 1 for process 2? I'm taking that exit time, subtracting the arrival time. That's 22. What about process 3? This is 42 minus 2. That's 40. What about process 4? 49 minus 3. 46. Very, very easy to do once you know what you're doing. Now that we calculated the turnaround time, we can calculate the wait time because it's the turnaround time minus the burst time. So I look at P1. How long did it have to wait before it could start? Well, 15 minus 15 is 0. It didn't have to wait any time whatsoever. What about the P2? Well, that is the turnaround time minus the burst time. What's 22 minus 8? That's 14. Then P3. How long did it have to wait? What's 40 minus 19? That's 21. And what about P4? How long did it have to wait? Well, 46 minus 7, which is 39. Now that I've calculated these wait times, I can add them together and I get 74. How many processes do I have? I have 4. If I do 74 divided by 4, that will give me the average wait time of 18.5 seconds. That is how first come, first served works. And the next scheduling algorithm is the shortest job first. Now, another one of the best approaches to minimize process waiting times. It is considered non-preemptive, unlike shortest remaining time first, which we're going to do next. Now, there is a preemptive version for shortest job first, but Computer Science 9618 focuses on the non-preemptive version, so that's what we're going to be looking at. Now, this means that each will run until it is no longer needed by the processor. They're going to arrive, the processor is going to identify the shortest job, and that's the first one to go. So the shortest job in the queue is the first to run. We're going to calculate the average wait time for these, as well as by finding the wait time of each process. So let's take a look at this example. Here we have 4 processes, process 1, 2, 3, and 4. The arrival time, they all arrived at the queue at the exact same time. So we're going to pull the shortest time first. Now, there is a preemptive version. Computer Science 9618 focuses on the non-preemptive version. That's why the arrival time is the same for all of these. So we got to calculate the wait time, which is very easy to do. So they all arrive. What is the shortest job here? Well, how do I know that? We look at the burst time. Which one takes the shortest amount of time to run? That would be P4. It has a burst time of 3 seconds. Enters the CPU at the 0 second mark, exits at the 3. So, how long did it wait before P4 could start to run? It waited 0 seconds. It started at the very beginning. It's what kicked off the whole thing. P4 is done. Now the computer looks at P1, P2, and P3. We can see P2 is the shortest amount of time we need. So P2 goes next. How long does it run? It runs for 4 seconds. Exits at 7. Now, how long did P2, here's our 7, how long did P2 have to wait? Had to wait just 3 seconds because P4 exited at the 30-second mark, allowing P2 to go. P2 and P4, both those processes are done. So now we have P1 and P3 to compare. P3 is next. How long did P3 have to wait before it had its turn? Well, it had to wait 7 seconds. How long does it run? It has a burst time of 9. It runs till 16. That leaves only one process left, which is P1 or process 1. How long did P1 have to wait? Had to wait 16 seconds because that's when P3 finished, and now it was P1's turn. It runs for 23 seconds and finishes at the 39 mark. I have the wait time here. You don't have to, you can calculate the arrival time, the exit time, the turnaround time, and the wait time, but you don't need to do that because these are the wait times. So I add them together. 3 plus 7 is 10. 10 plus 0 is 10. 10 plus 16 is 26. I have 4 processes. 26 divided by 4 is 6.5. That is the average wait time and how the shortest job first works. Let's take a look at the next algorithm. So now the last algorithm, shortest remaining time first. It's one of the best approaches to minimize process waiting times, and this is what we consider preemptive. Now, what preemptive means is that the low-level scheduler has the ability to remove a job from the running state and place it into the back of the ready queue so another job can go from the ready state into the running state. Now, you also have to include the arrival time where you're doing shortest remaining time first and take that into account. We're going to calculate the average waiting time again for this one because remember, that is what we are after. So let's run an example. So here we have 4 processes again, P1, 2, 3, and 4. We can see the burst time again, how long it takes to run. And this time we can see the arrival time, and that will play a role in what the waiting time is. So P1 arrives at 0. It's the first one to arrive and the time starts. Now, how long does P1 run though? It runs for 1 second. But why does it run for 1 second? Because P2 arrives at the 1 second mark and 4 is less than 22. You may be saying, well, where'd you get 22 from? Clearly here it says 23. Don't forget, P1 has run for 1 second. So now it compares 22 seconds of burst time with 4 seconds. P1 runs for 1 second. P1 gets taken off by the low-level scheduler, and so it can go to the back of the ready queue. So P2 goes. Now, how long does P2 go for? Well, after another second, at the 2-second mark, P3 arrives. So it's doing 9 compared to 3. Because remember, P2's been running for 1 second when we reach 2 seconds. At the 3-second mark, P4 arrives. It compares 3 to 2 because P2 has been running for 2 seconds. Because P2 is now the shortest one, it's going to run until it's done, which is the 5-second mark. So P2 is completely done. The computer says, okay, which one has the shortest remaining time? P1 has 22 seconds, because remember, it ran for 1 second right over here. P3 has 9 seconds, and P4 has 3 seconds. Well, what's the shortest? That would be P4. How long does it run? We don't need to look at any more arrival time because all the processes have arrived. P4 is going to run for a full 3 seconds to the 8-second mark. P4 and P2 are done. Now the computer says, okay, we have process 1, which has 22 seconds remaining. P3, which has 9. Which one's shorter? That's P3. It's going to run for a full 9 seconds to the 17 mark. Now P1 is the only thing that's left, but P1 is not going to run for 23 seconds. Remember, at the very beginning, it had already completed one of the seconds, so it's going to run for 22, which brings us to 39. Now that we have our chart, we're able to calculate the exit time. And remember, the exit time is when it leaves and not going back into the queue. So P1 left at the 39-second mark. P2, when is the last time we saw P2? That was right here at the 5-second mark. What about P3? The last time we saw P3 was right here at the 17-second mark. And what about P4? We saw it last right here at the 8-second mark. Now that I have exit time, I can calculate my turnaround time, which is exit time minus the arrival time. So here, what's 39 minus 0? 39. What about the turnaround time for P2? That's 4. What about P3? Well, 17 minus 2 is 15. And what about P4? 8 minus 3 is 5. Now that I have my turnaround time, I can calculate what I'm after, which is the wait time. And that's my turnaround time minus the burst time. 39 minus 23 is 16. I'm taking my turnaround time, subtracting it from the burst time. 4 minus 4, 0. Now I want to talk about why this is 0, because you may be saying, well, hold on. It didn't start at 0, it started at 1. But when did P2 arrive? It arrived at the 1-second mark. So as soon as it arrived, it was able to start. That's why it is 0. So then we have P3, 15 minus 9 is 6. And then we have 5 minus 3, the turnaround time of P4, minus the burst time of P4, that is 2. Now that I have the wait time, I can add them all together. 16 plus 0 is 16, plus 6 is 22, plus 2 is 24. Now that I have that, I calculate the average. 24 divided by 4 is 6. That is how you calculate the average waiting time, how you get the turnaround time, exit time, and individual wait times using those different scheduling algorithms. Hope you guys found this video helpful. If you did, make sure to give it a thumbs up and subscribe to help the channel grow. And we'll see you guys in the next review video.